Okay, design considerations. Yes, so we've talked about some of these already. What you can consider for your spacecraft design is the environment that it will see for the orbit that you chose for it. You can think about it in LEO. You can think about it in interplanetary and on planetary surfaces, for example. You should also think about the power dissipation from your electronics. You should think about geometric placement with respect to sensitive components in space environment. And you should think about how you distribute components that like to be hot or cold. So these last 2 points are demonstrated with this picture of the James Webb Space Telescope, where there are 2 sides of the James Webb Space Telescope. There's a hot side, which is facing the brunt of the sun, the solar radiation, and then there's a cold side, where this heat shield separates the hot and the cold side. So yeah, you can see this geometric placement in play here, where this hot side is facing the sun, the instrument and such as the detectors and filters are facing away. And you can see the distribution of components. So these, the solar panel, antenna, computer, and reaction wheels, those like to be warm. So you bunch them together. And then on the other side, the science instruments, the mirrors, they like to be cold. So that's where you would bunch them on the other side. Okay, and then there were questions. There were 2 people who caught that I said that you need to keep RTGs hot, and that is a mistake. You need to keep RTGs cool. So good on you for catching that error. And then there was a question about thermal cycling. Doesn't this happen every time orbiters enter direct sunlight, then pass behind a planet like Earth? Yes, this is true. Thermal cycling absolutely does happen every time a satellite transitions from sunlight to eclipse. Not all components are affected equally, though. Some components in the center of the spacecraft are more insulated from thermal cycling, whereas the outside is most affected. You can think of solar panels and antennas as being one of the more affected components. All right, we are on track. So answered all the questions. The last topic we'll talk about today is general arrangement and design drivers. I had a huge amount of help writing this section from the Spacecraft Thermal Control Handbook, which is listed there. You can check out this hyperlink to get the PDF version of this book. If you're interested in thermal engineering, I highly recommend this book. It was recommended to me by a NASA JPL thermal engineer, and it has a lot of practical advice. So I'll be essentially giving you word-for-word excerpts from this textbook. Okay, because we're talking about general arrangements, why not draw from past missions, from typical satellite designs? So here we have spinners. There are spin-stabilized satellites, and there are 3-axis stabilized satellites. So on the right there, we have a spinner satellite. Of all the thermal designs for spin-stabilized satellites, or spinners, the most common is the one typified by the Defense Satellite Communication System, DSCS, and a host of commercial communicating satellites. The design approach is to use the spinning solar array as a heat sink for the internal components. A cylinder spinning with the sun normal to the spin axis will be close to room temperature if the ratio of solar absorption to infrared emittance is near 1, as is the approximate case with the solar cells that cover the cylinder. Because of its temperature, the spinning solar array makes a convenient heat sink for internal components. This figure illustrates the thermal balance in a typical spinning satellite. Electronics boxes, usually mounted on shelves, radiate their heat to the solar array, and sometimes also to the forward or aft ends of the satellite if extra radiator area is required. The electronics boxes are typically painted black for high IR emittance and are mounted so as to ensure good heat conduction to the shelves. For most boxes, the combined surface area of the box itself and its shelf is sufficient to radiate the waste heat to the solar array without development of a large temperature difference between the box and room temperature away. Because most spinners are placed in high-altitude geosynchronous orbits, they experience no more than 1 eclipse per day, and those eclipses last a maximum of 72 minutes. During eclipse, the solar array temperature drops dramatically, typically from room temperature to a value on the order of negative 75 degrees Celsius. In this period, the temperature of the electronics boxes and other components also drops. However, because their thermal mass is very high, they do not cool nearly as fast as the relatively lightweight solar array. The result is that the spacecraft can often coast through the eclipse without falling below the minimum allowable operating temperature of the electronics. There was a question about, oh no, does it matter how the spacecraft spins? For example, is there data that shows that a horizontal axis rotation is better than a vertical axis rotation or vice versa? Yes, there is definitely importance in the axis of spin. So if we have, say, the sun is pointing in this direction and we have our spin axis like this, we can get that rotisserie. Whereas if we have the spacecraft pointing like this and the solar panels are on the outside, then it really doesn't matter. The sun is not facing the solar panels. It's not evenly heating the components that are mounted on the other side of the solar panels. So what you want to make sure is that the surface that you are heating is perpendicular or incident with the sun vector. But there's another part of this question where in the attitude determination and control subsystem, there are preferred spin axes, but that's related to dynamics and not temperature. So we'll just save that concept for later. But yes, it does matter what your spin axis is. Then there are 3-axis stabilized satellites where you're not just spinning about one axis like these rotisseries, but you have the option of controlling your orientation in 3 degrees of freedom. So you can orient in whatever way you want. The most common type of satellite today is a 3-axis stabilized variety, typified by the Tracking and Data Relay Satellite TDRS. The designs of almost all these satellites take the same basic approach to thermal control of the satellite body, insulating the spacecraft from the space environment using multi-layer insulation, or MLI, blankets, and providing radiator areas with low solar absorptance and high IR emittance to reject the satellite's waste heat. So let's just look at this a little bit. We've got this hexagonal spacecraft bus, and so you can think of that hexagonal structural wall where there are radiators on the outside. There are MLI blankets also coating the outside of the spacecraft bus. The surface finishes and insulation control the appendage temperatures like the antenna and the solar arrays. The heaters are inside to protect equipment when the satellite is in a low power mode. Okay, yep. Oh, there was another question about rotation. I think the question is, how quickly would a spacecraft need to rotate to ensure that its components are being evenly warmed? It does matter. It does and it doesn't. The dynamics of a thermal system are very slow. There's this concept of thermal mass, or you can think of it as like heat capacity, right? How much energy per degree temperature change. And you can think of thermal systems as having large masses or inertia, so resistance to change compared to the dynamic motion of a satellite. Like, is a couple degrees per minute versus a couple degrees per hour going to matter for a satellite? And I want to say not that much. But yeah, do a detailed analysis of it, because my intuition is that the timescales of thermal systems versus dynamic systems are a magnitude different. So my intuition is it doesn't matter that much. I mean, it certainly does matter that you're rotating at all. So yeah, intuition doesn't matter that much. And then there was this really silly question, has anyone tried cooking a chicken in space? I think it would not be a very cost-effective way to get a rotisserie chicken when we have a Costco option for $5. But no, I can't think of a chicken in space. Fun fact, there is the idea of replicating chickens in space. It's the idea of automata. Anyway, off subject. Other thermal design examples in spacecraft. So instead of just large systems of spacecraft, let's talk about components. So batteries are very sensitive. From the power system chapter, we learned that there are a lot of requirements surrounding batteries. They're very thermally constrained. So because we care a lot about batteries, there's going to be a lot of thermal control surrounding them. Let's go through a case study. This is an older type of battery called NiCad, because the year this book was published was 2002 and battery technology has changed. But let's just look into it. So NiCad batteries usually need to be maintained at a temperature between 0 and 10 Celsius to maximize their life. As their temperature rises above this range, their maximum useful life decreases significantly. Below this range, the electrolyte may freeze and damage the battery. Another requirement common to many types of batteries is that all batteries on the spacecraft and all cells within a battery must be kept at the same temperature. This isothermality requirement is necessary to ensure that all cells charge and discharge at the same rate. Although some NiCad batteries are mounted inside spacecraft and simply painted black to radiate the waste heat from charge and discharge inefficiencies to the spacecraft interior, the most common battery thermal designs use radiators and thermostatically controlled heaters, as seen here. So we've got a radiator here. We've got heater here. And those are the batteries. You'll note that on the Artemis CubeSat kit, we have Kapton heaters that we mount to the battery surfaces. Here are other designs for batteries. Here's a question. Does the thermal system is distributed and integrated through the spacecraft? Does this mean the thermal subsystem is usually finalized last? And I would say that's pretty good intuition. From my experience, it's the structure system and the thermal subsystem that get finalized last because they just have a ton of little tweaks coming in and out, in and out. Okay, let's talk about antennas. So the thermal control requirements for antennas are usually to maintain temperatures within the allowable ranges for the materials they are made of, and especially for reflectors to keep thermally induced distortions within acceptable limits. For most antennas, an acceptable design can be developed using paints, insulation blankets, and/or low coefficient of thermal expansion structural materials. So here we'll see just typical antenna designs where you can have like a mesh reflector or a solid reflector. But what do these reflectors look like? How do thermal subsystems affect the design? So these reflectors can be made out of gold mesh. They can have graphite ribs and bare aluminum edges. On the frame, it can be painted black. There can be surfaces that are covered with MLI or with paint. Yep, so a lot of like surface finishes here and material selections. let's see. So I only have 5 minutes left, so I won't go through this whole thing, but I'll just answer this question. Space is very cold. This is making it unclear whether we are looking for sources of heat or ways to vent. Exactly, bro. It's unclear. So you need to do analyses to see if components run hot or run cold, because there is that balance of heat coming into the system from the space environment, but also your spacecraft shedding heat, radiating into the space environment, just like a black body. Because of that, it is unclear, and you need to look into the nuances. Okay, finally, no, this is the second to last slide. There are devices that probably need to be cooled. Some spacecraft payloads require cooling to low temperatures. The most common types of cooled instruments include IR sensor, focal planes, and optics, as well as low noise amplifiers for RF receivers. Several devices are available for cooling such applications, including radiators, stored cryogen cooling systems, and refrigerators. Here we see something called the Defense Support Program, DSP satellite, using a system of radiators to cool the optics and focal plane. The optical components, the mirrors, and the telescope enclosure and baffles are cooled passively by covering the telescope enclosure with low absorptance, high emittance quartz mirrors. Cooling the optics and enclosure reduces the amount of IR radiation emitted from those surfaces. The operating principle of the system is the transporting of heat from the focal plane and phase change material to the radiator by means of a pumped helium loop during the half of the orbit when the sun does not shine on the radiator. Cool. Lastly, let's talk about solar arrays. Thermal control of solar arrays is generally straightforward. The solar cells preclude the use of any thermal finishes on the sun-facing side of the array, so the array's thermal radiative properties are controlled by the high absorptance, high emittance solar cells themselves. To keep array temperatures as low as possible, a practice that increases electrical efficiency, designs usually call for the back end of an array to be painted with high emittance black or white paint. The white paint is used primarily in low altitude orbits where albedo loads from Earth may illuminate the backside of the array. As the result of their high absorptance, high emittance, large area, and low mass, solar arrays typically cycle through wide temperature ranges as they travel from sunlight to eclipse, plus 65 to negative 75 degrees C in low Earth orbit, and 55 to negative 145 C in geosynchronous orbit. I just have a picture of a front side and back side solar array for the Dragon capsule, just to demonstrate that this is definitely used in practice.